Alright, so the next concept is what is internet. So every company has a network. Every organization has a network. When you connect many networks, that is called the inter-network. So inter-network is basically a network that connects many networks. And today, we don't know how many numbers, but this July 2008, they had 600 million hosts. I would not be surprised if it is now multiple billions of hosts in the internet. And a company that provides the service is called ISP, Internet Service Provider. Can you name an ISP? Yeah, AT&T. And so they provide access to the internet. And the telephone companies are examples of ISPs, AT&T, Verizon, Comcast. And Comcast is not a telephone company, but they are also ISPs now. They are the video service provider, right? And then the coffee shops. So most of the coffee shops provide internet access, so they are ISPs. So the way internet works is that you have enterprise networks, then you have access, and then you have core. And these are also called stub networks. Stub networks, because they don't do any interneting among themselves, whereas these things are connected to many other places, and then they transfer packets. So these people's job is to transfer packets for others, whereas this one just does it for itself. So they are more like user, and these are more like the service providers. So this is stub network. It's privately owned, not owned by ISP, and this is owned by ISPs. Access network is the one that goes from the users to the ISP, and then core is one which goes inside the ISP. ISPs are many different size. Big ISPs are called Tier 1. They provide services to Tier 2 ISPs. Tier 2 ISP provides services to Tier 3 ISPs. Tier 1s are like AT&T and Verizon. These are national providers, global providers. And then Tier 2 might be regional providers. So there are many companies which just rent facilities from AT&T. Or actually, even if they don't rent facilities from AT&T, they might use AT&T's circuits for going from one city to the next. So they are Tier 2, and then Tier 3 is local. Some people, they will just provide a small area service, and then they will use Tier 2 to handle the traffic going outside. So this is basically the size of the company: Tier 1, Tier 2, Tier 3, small, medium, and large. The enterprise networks use two technologies mostly: Ethernet and Wi-Fi. We used to have different things before, but nowadays those are the two. Most of you have just Ethernet and Wi-Fi, right? Ethernet uses the unshielded twisted pair. This one we have seen, and it runs as 10 megabits, 100 megabits, 1 gigabit, 10 gigabit. Has anybody got 10 gigabit? No. Does anybody have 1 gigabit? Yeah, almost all of you. The thing is, if you buy a laptop today, it will come with a 1 gigabit port. This laptop is new, it has 1 gigabit port. If you take an old laptop, it might have 100 megabit port. If you take an older laptop, it will have 10 megabit port. So as you can see, with every 5 years, we come up with a 1 factor of 10. Or every 2 to 4 years, we come up with a factor of 10. So the speeds are going up. So you would not be surprised if 4 years from now, you had 100 megabit, or 10 gigabits. Okay, they're working on that. So 10 gigabit is used right now today, but that is used mostly, inside the companies. So, for example, Vashu might have many 10 gigabit routers and switches, but you don't get to the desktop. It doesn't come all the way to the user because it's kind of expensive. But in few years, it will become cheap enough so that your desktop will have 10 gigabit. Originally bus, but now point to point. So this was the original Ethernet, but this is the today's Ethernet. Wi-Fi is called 802.11, IEEE standard, and it uses 2.4 gigahertz and 5.8 gigahertz. Those two frequencies. It runs at those two different frequencies, 2.4 and 5.8. And all of you have seen Wi-Fi, so I don't have to say too much. Access networks. In the access, the telephone company provides you access by many of these methods. Dial up. If you have nothing else, you can just dial in, right? Many of you, I mean, at least I remember using dial in before. DSL is the next step. You can get a DSL service. Cable also you can get, or fiber to the home. So now I have fiber to the home. Actually, I don't think it is a fiber, but anyway, what I have is UVerse service, right? UVerse service is fiber to the curb, not fiber to the home. So the fiber comes to the neighborhood, and from there they just send it by copper. Fiber to the home is another possibility. Wi-Fi is another possibility for getting the access, and WiMAX is something that is coming in. So WiMAX is a new wireless technology which runs at much higher speed, but which goes for much longer distance. Actually, let me put it this way. So it goes 5 kilometers. Wi-Fi goes only 100 meters. If you put a Wi-Fi transmitter, you cannot get into the next building. In my home, I can't even get Wi-Fi outside of my home from inside. So it goes very limited distance. But WiMAX covers the whole city. All right. So that's coming up. So this cartoon is about a slow Ethernet connection. And Ethernet connection is always internet connection is always slow. So we have gone up actually in capacity. I remember getting 56 kilobit on. Now today we are at 18 megabits, which feels not very fast. In Japan and Korea, they are at 100 megabits. Okay, so they are ahead of us. I mean, we haven't heard of 100. Has anybody got 100 megabit? You see, I mean, there is, but this is a long question, so I will not answer that question right now. Why we are far behind? This is a political question. But interesting part is that, and I wanted to share this story with you, that after having every country wanted to get ahead in technology, and right now the best way to get ahead in technology is to have the best communication technology, which is the internet. So every country spent a lot of money trying to get the latest technology first, and really Korea and Japan do much more in this respect, followed by China and other countries. So Korea, Taiwan, and Japan, they are always ahead. So if you go into wireless, as you talk about wireless or anything else, they try to do it first. And government gets involved. So the government puts money into getting that done faster. Here, the government doesn't get involved. So that is one reason. It's only the companies can do whatever they want to do. There's no government incentive. So the idea is there. I also want to share this story because it's interesting. Is that in Korea, after 10 years of very high-speed internet, they found out that there's a big problem. And the problem is, what do you do with 100 megabit at home? Well, you can play much better games. You can play the games that you cannot play with 10 megabit. You can really, shoot very far and everything else. So they found that the students are not learning anything. They're staying home much longer, and they're staying at video games. And so now they're cutting down on speed. They're cutting down that basically, because too much of this is not very good, okay? All right. So dial-up. The way dial-up works is that you dial a computer, your computer has the digital bits, you connect it to a modem. Now I think for most of it is history, but I just want to tell you because we went through this style. The modem will make the bits in a sound, in voice, and that will go over the wire to the phone company. All right, and then the phone company will convert that sound back into bits. So your modem will digitize it. Will convert the digital bits into some continuous sound waves. And because the access was all analog, only analog circuits can go there. So basically, and the phone company, inside the phone company, the core was all digital. So they would convert that back into bits, and then they will send it to wherever you want to go. And their end, they will do the same thing. Is that they will convert back into voice, and then. So right now the access is digital. Access is digital, so the bits can come from phone company to your home, but they're coming in the wrong form. Well, not really. I mean, there's a little bit more overhead in ATM, and it is little more cost in ATM, and so that's why they will convert to Ethernet someday, but I don't think speed will change much. So anyway, in the phone company days, old days, when we had really the modems, the access was analog, so the only way you could get to the phone company is by voice, and so we needed a modem to convert your digital bits into voice. So that's how it worked. A modem is modulator, demodulator that converts the electrical bits to sound waveforms, and then the telephone company, they're designed to carry only 4 kilohertz voice. So that was another limitation. Basically, when the phone company wanted to design their wires, they had to decide what quality wire they should have, and they conducted a test. And they found out that if they can pass 4 kilohertz, then people are happy. Now with 4 kilohertz, you would not really be able to send music. So nobody sends music over the telephone company's wire. I mean, really, it doesn't sound very good if you hear some song on the phone, right? So it was not designed for that. It was designed only for normal communication, right? For music, you need 20 kilohertz at least. But anyway, and so with 4 kilohertz, you could only do up to 56 kilobits. So that is where the modem stopped, and then we had to move on. So the question is, I have used the word hertz bits, and I thought I will put something explanation as to what these are. The book doesn't have this, so please listen to this carefully. Bits are what we say, 0 and 1, binary bits, right? But to transmit a 0, how do you transmit a 0? To transmit a 0, there are many ways. You could do it that I will send plus 5 volt for 1 microsecond, and then I will send minus 5 volt for 1 microsecond, and that is a 0. And for 1, I will do minus 5 first and then plus 5 later. That is 1. And that's actually a transition which is used, what we call coding, that is used in many places. Okay, where a 0 is a transition down, a 1 is a transition up. So we just look at what is happening in the middle. If we see that the voltage is going up, that is a 1, the voltage is going down, it's a 0. Yeah, you could send 2 zeros at a time. That's not a very difficult problem. You could just keep sending the same waveform again and again and again. In the beginning, we know exactly where the bit begins. So whenever any circuit comes up, like even your Ethernet, when you connect, there is something done to make sure that you know exactly where the bits begin. 0 and 1. Sitting is send that first sequence and then send the second sequence. It doesn't matter what you send, because in the middle we are just going to check. You could send 0, 1, 1, 0, 1, 1, 1, anything. This is 1 bit, this is 1 bit. Both of these are bits. Right? However, when you send a signal like that on the wire, actually all these are going is sine waves. Right? So this waveform might translate into some sine waves, which we do not want to get in here right now, but basically the frequency of that sine wave is what we call hertz. How many cycles per second? So this one, for example, is, if this was 1 second per bit, you will have 1 cycle per bit. And what about this half thing here? This one pulse, little pulse here. That is called a baud. And so this will be 2 bauds per second, the smallest pulse that you have to send. Now let me tell you why we worry about the bits, baud and hertz. Because the sender cares only for the bits. The sender wants to send as many bits as they can send. Right? They want to send 2000 bits or 10 megabits or 10 gigabits. Sender only wants to send bits. But the receiver cares only for the baud, because the receiver has to be able to distinguish this little piece that it is up, and then in the little time it has to determine that it is down. So the receiver is limited in how many bars it can receive. Right? If I make that 1 nanosecond, receiver cannot receive. Receiver says, sorry, I just can't figure out in 1 nanosecond anything. Right? So the receiver has to worry about the smallest pulse that appears in the signal. Oh, okay. So it can be a bit. A baud could be a bit. For example, another coding could be that 0 is 0 volt and 1 is 5 volt. Right? Anytime you have a 0, 0, and this is 1. But that has its own problem, which I will not go into here right now. But so there are many reasons. A whole lecture on coding which we can give, but right now I'm not going to give that. But that's not coding. This is a coding. This is much more useful coding. 2.4 gigahertz. Actually, it's like don't worry about wireless, because in wireless there is two kinds of okay, there are two problems. One is that 2.4 gigahertz is what we call the carrier, and then that is modulated with these things, and the modulation itself is only 56 megabit or 11 megabits or something like that. So we are talking about the modulation here. And this is what you brought up, is that this is translated into this right now waveform, and then this can be sent using another wave. So that's a whole physics which we don't want to get into, right? So yeah, so in Wi-Fi when we say 2.4 gigahertz, that is not 2.4 gigabits or anything like that. The bits are only few kilobits or few megabits, and so this is only few kilohertz, but then this is modulated on a carrier which is 2.4 gigahertz. Alright, so let me just repeat again, and this is important because it's not in the book, but it's in the exam for sure. Bits are zeros and ones that you want to send, and the sender cares for it. Bauds are the smallest pulse size. There is another coding in which a zero is let's say 1/2 microsecond followed by 1.5 microsecond of low, okay, high and low. In this case, this is one bit, this is one baud, not that one. This is the smallest pulse that you have to send, the smallest time duration that the receiver has to worry about is the baud. So in this case, it is 1.5 microsecond, this is 1/2 microsecond. And so 1/2 microsecond is what the user has to worry about. In some coding, they take 2 bits and then they make 4 pulses. So this is 0, 0, this is 0, 1, this could be 1, 0, this could be 1, 1. Right? In this case, this is the baud, and if this is 1 second, you have 1 baud, right? But there are 2 bits per second. Does that make sense? I mean, like, you know, so basically the number of bauds and bits could be more or less. Hold on. This has to be clear to everybody. That you could take multiple bits and represent them by 1 pulse. When a baud is unit like a meter, I mean, you know, yeah, so standard unit in the sense that you cannot say the baud is always 1 second. The thing is, baud means 1 pulse per second. Now here's another interesting thing is that when you say bits, we have to say bits per second. For hertz, we don't say hertz per second, because hertz has a second built in. Right? When we say 15 hertz, that means 15 cycles per second. Right? Similarly, bauds, when we say baud, it is, you know, when we say it is 15 baud, means 15 pulses per second. Okay, so I said many things. I just want to make sure that everybody understood this. Baud is the basically inverse of the time of the smallest pulse. So if this pulse is half second, this is 2 bauds. If this pulse is 1/2 microsecond, then it is 500 kilobaud. Okay, so baud rate is inverse of the time of the smallest pulse in the coding. Alright, so the receiver cares only for the smallest pulse, and the pulse is measured in, you can measure it in seconds or you can measure it in baud. They are just opposite. 1/2 millisecond is same as 2 kilobaud, 1/2 microsecond is same as 2 megabaud. And the wire cares only for the hertz. By the way, wire is designed for a particular hertz. So there are 3 people, sender, receiver, and the wire. The wire is designed for a particular hertz, so you cannot, so it is fixed. So if the wire is designed for 4 kilohertz, you cannot, anything more than 4 kilohertz will be blocked by the wire. And so what will happen is you have to design your coding such that if you want to send, you can send 8 kilobits through a 4 kilohertz wire. Alright, how? You have to design so that 2 bits require only 1 cycle. Right? Or 3 bits per cycle. And so this is a coding game, and there are people whose full-time job is to design coding, and they are working very hard because now we are able to send today. On the wireless, it is particularly important. Today in the wireless, we can send about 6 bits per hertz. We cannot send 7 or 8 or 9 or 10. Actually, some places we can, probably with a lot of money. So tomorrow they will discover how to send 7 or 8 or 10 bits per hertz. Then we will have even faster wireless. And that's how this WiMAX and Wi-Fi, etc. are working, is that they're discovering better codings so that number of cycles remain the same, but more bits can be sent. So, okay, so you're saying Wi-Fi and WiMAX has nothing to do with the signal strength? Yes, signal strength is the issue. So you can put more power and then you can go longer and things like that. But that, there is a limitation there too. I mean, you cannot put too much power because otherwise people will get burnt. I mean, you don't want to stand next to an antenna which is transmitting microwaves. You will get cooked. That's what microwave is, believe it or not. It's the same microwave, except that the microwave that you that you use in cooking is 700 watt or 700 kilowatt or something. It's not 700 kilowatt. It's 700 watt power, right? But the microwave tower that you stand next to is only, milliwatt or microwatt. Okay, this antenna, this is transmitting right now. This is my laptop. This is an antenna, microwave antenna. It is transmitting few milliwatts. Basically, everything is a cost. So when you have multi-level coding, then the receiver has to worry about distinguishing 2.5 volt and 5 volt, right? And then if you have 4 levels, then you have to worry about 1.25, 2.5, 3.75, and 5 volts. And remember, these levels, as the signal goes through the wire, after some distance, they become totally different. So the receiver has to do all that tough job. So it becomes more expensive. So the more levels you have, more difficult it becomes. The speed of transmitting 1 baud. Yeah, 1 baud means 1 pulse per second. 2 baud means 2 pulses per second. 100 baud means 100 pulses per second. You can have any number of bauds, any number of bits, and any number of hertz. It is not necessary that for 4 kilobits you need 4 kilohertz. You could do 4 kilobits using how many hertz? 8 kilohertz, 20 kilohertz, or 1 kilohertz. Depends upon the coding. Similarly, the baud and the bit relationship. You could do any number of bits with any number of bauds. And so on and so forth. There are 3 different things and 3 different limitations. The receivers care for what? Baud. The senders care for what? Bits. And the wire cares for what? Hertz. And so if you want to get more hertz, you need a better wire. If you need to have more bauds, you need a better receiver. If you need more bits, basically that's always good. So I mean, this basically I'm saying that the cost goes up when you increase any of these. All right. So here's an example, another example. This is a simple coding. 0 is a low and 1 is a high. This is called Y-level coding. 0 is a plus 5 volt. Sorry, 0 is a 0 volt, 1 is a plus 5 volt. This one will have how many bits per cycle? Yeah, 2 bits per cycle. And how many bauds per bit? 1, yeah. Now here's another coding, which is the one actually I wrote on the board. This one is 0, 0 is the lowest level, 0, 1 is there, and 1, 0 is here, and 1, 1 is that level. Okay? So now, this cycle, as I said, is misleading little bit because this is a possible cycle, but the worst case cycle would be the one that I wrote on the board here, where you could have just high and up, and all that. So this will have 4 bits per hertz, sorry, 4 bits per hertz, and then it will have 2 bits per baud. Okay, so this is what I was saying was that the signal, when we design these codings, we don't know what people will be sending. So we cannot just design so that people will be sending 0, 1, 1, 0, 1, 1, 1, 1, 0 like this, right? This sequence. So if somebody sends something else, the waveform will look different. And we want to design for the waveform that requires the maximum number of hertz. And this is the waveform, which is that somebody just sends the high level and then the low level and then the high level and the low level. If you do that, that would be like somebody sending 0, 0 and then 1, 1 maybe. And then 0, 0, 1, 1, 0, 0, 1, 1. That way you will have to cycle very fast. And that is, even that, it is 4 bits per cycle. What is a cycle? Cycle is going, just one waveform, right? When you say a sine wave, cycle is going up and going down and going back to 0. So starting from a 0, going back to 0. So basically, so we are not talking about cycles, we are talking about hertz. Hertz is a cycle per second. So when we say 100 hertz, means 100 cycles per second. And some wire can carry that, some wire cannot be able to carry that many hertz. So when we say, let's say you have 500 hertz. So each cycle is how long? Seconds, right? 1 upon 500 seconds is 2 milliseconds. So cycle is not a second, cycle is different for that one, right? Given any coding, you try to draw a waveform that the user can send. So with this one, if the user sent this waveform, this is one cycle. One cycle is this long. Actually, let's start from here, and one cycle is this long. Right? And how many bits are sent in that cycle? Red part? 1, 2, 3, 4, 5, 6, 7, 8, 16 bits were sent. So one could say, well, there are 16 bits per cycle, but that's a very good case. That's the best case. Somebody could just send 10, 11, 1011. In that case, you will be cycling basically they could be sending the lowest and the highest, lowest and the highest, lowest and the highest, lowest and the highest. Then in that case, each cycle will have 4 bits. Each 2 bits is in one pulse. Now, you could do any number of seconds. It could do in 1 microsecond, you could do it in 1 second. Depending upon what is the unit, you will have to have that many cycles per second. We define baud as how many bits in 1 second. We define bauds as how many pulses in 1 second. How many pulses, not bits. How many pulses? So here, each of this is a pulse. If this was 2 microsecond, how many bars is that? Okay, let's make it easier. Each pulse was 2 seconds. How many bars is that? Half bar. Because each pulse is 2 seconds. So how many pulses per second? Half a pulse per second. If each pulse is 2 seconds, we have half pulse per second.